So today we shall see something very interesting, something with which you might be able to relate in a more tangible manner. So you remember a few lectures back we had introduced these two terms, the Hamiltonian and the momentum, and they didn't seem to make much sense because you're used to seeing momentum in a particular form in the context of mechanics. But the way we are presenting this idea of a momentum up until this point doesn't seem to be able to relate to that idea of a momentum, because after all you're looking at a curve, a function, static function, right? Whether it's the equation of a catenary or it's the brachistochrone, these are all equations. So what has it got to do with momentum? So hopefully by the end of this lecture you'll be able to see why the term momentum is indeed justified. So this development that we are going to present today is due to Hamilton, and it came into being several years later, much later than the development of calculus of variations. And in fact, within this formalism are the seeds of the very important idea of the maximum principle, which was only discovered in the last century, in the 1960s. And it turns out that if people had the perspective to view the Hamiltonian formalism with a certain amount of a tweak, then this idea of the Pontryagin's maximum principle would have been very apparent perhaps centuries back. So we shall try to trace all of that and see how to connect these dots, right? So again, recall that we have the following. Right, so this is the objective function or the cost function null that you had to minimize, and we define the following. What was that? If you recall the momentum, what was its definition? The partial of L with respect to which one? Which one of its arguments? Third argument, right? Y prime. Right? And now here's how we are going to write this. Okay. Of course, the Hamiltonian is still going to depend on x, y, y prime, and now we're going to use this variable p that we have just defined, the so-called momentum. And how do you think this fellow is going to look now? There was obviously a dot product. In case of a scalar, the dot product doesn't matter, it's just multiplication. But in general, it was a dot product between what and what? Y prime and Ly prime, isn't it? But now Ly prime's got a name and a symbol to go with it, which is P, right? So this is Y prime dot P minus L. Again, I am omitting the dependencies, the arguments, for the sake of brevity. Yeah? This is just the definition, the setup. We haven't invoked any conditions on optimality yet. We know that a necessary condition for the optimality is given by the Euler-Lagrange equation, right? Okay. Now what? We are going to try and derive the so-called canonical equations according to Hamilton. Okay. So our variables of interest would be p and y, the momentum and the position. Yeah, you can think of it like y is the curve that tells you your position. The moment I give you an x, if you know y, you know the xy coordinates. Okay. All right. So if I were to do the following, the partial of this fellow with respect to y, what do you think that's going to lead to? It's a partial, remember? So only those terms which have explicit appearance of y will show up something non-trivial, perhaps. The other terms where y does not appear explicitly, they will lead to 0. So which part of this Hamiltonian that we have defined perhaps depends explicitly on y? This is basically two terms here, right? The difference between two terms. If you look at the first term, does this explicitly depend on y once you have defined it in terms of the so-called velocity? Okay, velocity doesn't make sense yet. The slope of y and the momentum. So all that you will have is minus the partial of L with respect to y. Yeah, you agree? This is just, let's make this explicit at this point with the arguments and everything. But what is this object? Like we have defined just 2 steps back, this is nothing but the negative of the momentum, right? How? Is it the momentum though? What is this? What condition connects this and this? Sorry? The Euler-Lagrange equation. So this is not just about any curve. If you consider this along the optimal curve, which means essentially that you're going to consider y is equal to some candidate optima, which is an extremal essentially. An extremal means one that satisfies the Euler-Lagrange equation. What do we know about that? Recall that the Euler-Lagrange equation is the following: d dx of L y prime is equal to Ly. So if you take a minus sign on either side, you get minus of this. But this object in turn, sorry, I should, yeah, be a little careful about this so that this object is sitting right here. So it's the d dx of the momentum, right? So this fellow is negative of the derivative of the momentum with respect to x. You agree? After invoking the Euler-Lagrange condition. Is that clear? So this is equal to minus, of course, along an optimal curve or an extremal curve at least. An extremal candidate is how I should call it. So this is minus p prime. Yeah? This is clear? Great. Let's do something else now. Because now this is defined in terms of these 4 arguments. If we now take partial with respect to p, what do you think is going to come out? Is there any p dependency here? Of course not. It's a function of x, y and y prime. So this one ceases to matter when you take the partial with respect to p. In fact, this one is also independent of p. So when you take the partial with respect to p, think about the scalar case, the dot product can be thought of analogously. This is just y prime. Yeah? This is quite easy to see. In other words, what we have just derived are the following two equations. P prime is equal to minus negative of the partial of the Hamiltonian with respect to y, and y prime is the partial of the Hamiltonian with respect to p. Okay, and these two are called the canonical equations. Under the Hamiltonian formalism, these are the canonical equations of Hamilton, okay, satisfied by extremals. So in lieu of the Euler-Lagrange conditions, if you have knowledge about the momentum and the position, then the dynamics of the momentum and the position, of course dynamics doesn't make sense unless you think about them as functions of time. We shall shortly make the transition to make things clearer, but the propagation of p and y are governed by these equations. Yeah, and we have used the Euler-Lagrange condition here, so of course this is only true for extremals. Okay, all right. In the light of these things here, we shall now again revert to those two special cases that we had considered for the Euler-Lagrange conditions. One was the no y case where y did not appear explicitly in the Lagrangian, and the other was the no x case where x did not appear explicitly in the Lagrangian, and see if something can be said along similar lines. Because remember, the conditions we had there were, in one case the momentum was conserved, in the other case the Hamiltonian was conserved. So now that we have these equations and we have these dependencies in terms of the Hamiltonian, we should be able to see them more clearly. Yeah, we should be able to revert back to those conditions again. So let's see. Let's consider first the no y scenario. If there is no y appearing here, sorry, okay, in the Lagrangian, so this one is only a function of x and y prime, right? There's no y appearing here either. Yes, so what happens then? What happens to this term? Yeah, so we observe that you have to put the argument suitably, no? The Hamiltonian in this case will be y prime x px minus L as a function of x and y prime, right? Yes, just to make things clearer. So what do you think is this going to lead to? Is there a dependency on y here? No. Is there a dependency on y here? No. So this is going to be 0. Yeah. On the other hand, just a while back, according to this canonical equation, what do we have here? That's exactly the rate of change of the momentum, and that's 0, right? This implies that p prime is equal to 0 using the canonical equation. Does this agree with what we had derived the other day, which is to say that the momentum is conserved or remains unchanged? Yes, so this means p is constant with respect to x. It's an invariant subject to your shifting of x. Yeah. Okay so far? So at least this agrees with what we have already seen the other day. What about the no x situation? I hope I can erase this part, right? Part in the middle. Let's look at the following. Remember what was h a function of? X, y, y prime, p. Which one goes off now in the no x situation? X has to go off, right? X has to go off from which term here? Does it go off completely from the Hamiltonian? Well, because the p is a dependency, p has a dependency on x, the y prime has a dependency on x. The no x does not imply no x in the Hamiltonian, the no x implies no x in the Lagrangian. Yes. So this is still ddx of the following, which is y prime dot p minus, here of course you understand these have dependencies on x, but in the Lagrangian you don't have x anymore. So this just depends on y and y prime. Right? So what happens now? The chain rule, apply the chain rule here. You know this is an extremal candidate, so y double prime, the existence thereof is not under question anymore, like we have established some time back. So this is what? Y double prime dot p plus y prime dot p prime minus partial of L with respect to y times y prime minus partial of L with respect to y prime times y double prime. And what is that? What is this object? By definition, I have erased it from the board now, but by definition, what is this object? It's P, right? So this object is P. What about this object? Yeah. What can you say? See, this is P prime minus Ly. And that is, Ly is y. The first term in the Hamiltonian is P dot y prime. No dependency on this, right? So P prime is essentially, in terms of the Lagrangian, what exactly? Ly, right? So now these two cancel each other out. No, you take the y prime common, dot product with P prime minus Ly. But P prime is nothing but Ly itself. Isn't it? Is that clear? If not, please ask why this is. It's important to understand this, right? Because this will immediately then lead us. So this term and this term get chopped off. Very clear? Just straightforward here. I'm saying the other term, so this is P prime minus Ly dot y prime. And I'm saying this is also 0. Is it clear to everybody why this must be 0? Look at the canonical equation here. The first term in H was P dot y prime, none of which depended on y, and therefore when you took the partial, it anyway gave us 0. So the partial of H with respect to y only constituted the partial of L with respect to the same. Yeah. So this is also 0. This part of it is 0. In other words, the derivative of the Hamiltonian with respect to x is 0, implying that constant with respect to x. Yes, which is exactly what we had inferred from the Lagrangian expressions the other day with the no x and the no y situations being invoked on them. So in one case when you have the no y situation you have the momentum being constant, in other case when you have the no x situation you have the Hamiltonian which is conserved. Yes, can we proceed to the next part? You're clear on this? Okay, great. In fact, if you look at this, whole thing as a situation here, in deriving this whole expression, this condition that dh dx is equal to 0, yeah, where did this no x play a role? In the fact that this term did not have an explicit x dependency. If it did, then you would have had to have the partial of L with respect to x as well. That's the only term that is missing here, and that allowed me. Otherwise, the rest of it is just 0. Yeah. So you must understand at which point it is playing a role. The other relations, many of them still hold even in the general setup, like the definition of the momentum, its partial with respect to h and all those things, they will still be true. Because this equation is true irrespective of whether it's the no x situation or the no y situation. Yeah, and therefore this, the fact that this is 0 is also going to be true. The fact that the momentum is equal to Ly prime is true from definition. So this part would have vanished anyway. You would have been left with an extra term here due to the dependency of the Lagrangian on x. Because it is not there, so you manage to infer that this part is 0 and the other part doesn't exist in this situation. Yeah. So it's important to know why it works in this manner. So in general, what would happen? You would have this differential equation in terms of the Hamiltonian leading to something showing up as a partial in terms of the Lagrangian with respect to x. Okay, good. Now let us try and understand this in a slightly different fashion. Okay, let us just say, for no rhyme or reason whatsoever at this point, we just take the following. What do you say about this object here? Again, revert to the, flip your pages and see the definition of the Hamiltonian and tell me what this should lead to. Would it? Why so? Why would you say that? The first term contains P dot product with, yeah, y dash. So when you take the partial with respect to y dash, you are left with P. And the second term is the Lagrangian, so the partial of the Lagrangian with respect to, yeah. So this is again from the definition, yeah, no special case, like x, y, all of those fellows can be present in the Lagrangian's arguments, and this is still 0. And this is where the seeds of the maximum principle lie buried. We just have to dig it out a little from here. Okay. Of course, we are assuming that all these differentiations that we've carried out, these partials and all, they're smooth enough so that even partial differentiation can be done, right? In certain cases, they may not be feasible. These differentiations and derivatives may not be feasible. So let us think about it in a slightly different manner. Now that we are within the Hamiltonian formalism, I'll again write down the expression for the Hamiltonian at the cost of being repetitive. This is P. Now this has 4 arguments typically. Let's say that this particular argument, this third argument, is something I can choose. What does that mean? It essentially means you fix up an x the x coordinate, you fix up the y coordinate, yeah, and you have a certain velocity, that is y prime, which helps you define the momentum. So now the momentum gets fixed, but this y prime, let's say you are allowed to play around with this as if this is a decision variable. Let's say we replace this with a xi. You see, in the momentum, when you define it, you still have to use y prime. Yeah. So what I'm saying is that the definition of the momentum, which I've erased from there, I'd written right at the beginning, the definition of the momentum was, yeah. So in that, the argument was still x, y and y prime in the Lagrangian and its partials. So this one still uses y prime, but that lies hidden within. However, in the Hamiltonian's explicit expression, wherever the y prime appears independently, this is the key, independently, there I am going to consider it like an independent variable. So I am now just going to look at the Hamiltonian fixed at a point in space, say x and y, with a certain momentum that's also been assigned to it, yeah, and let's say I am along an extremal, I am moving along an extremal, okay. Then there is this Lagrangian here, the x here, the y here, and this free variable here. Is this clear? The point is, this fellow is, what is this fellow? Okay. So don't imagine for a moment that here also the y prime gets replaced by xi, because xi is a free variable that I am allowed to play with as an argument of the Hamiltonian, not in the momentum term. The momentum is still going to depend on x, y, y prime. So the momentum gets fixed up accordingly. So it's like I am sweeping over all possible choices of this third argument. Okay. The Hamiltonian has 4 arguments. The p gets fixed up. So the p implicitly within it contains the dependency on y prime. Now I am saying that the independent variable in the Hamiltonian, which appears as y prime here, the third argument, let me sweep over all possible choices of this. Okay. Now what do you think that's going to lead to? This is an independent variable, again, please remember. Okay. So if you take and evaluate it along an extremal, okay, what happens? First term, it's very similar to what we've just done just a while back, in fact here. Because the xi is not contained in herein. So it's just p, right? What about this? The xi isn't contained in these fellows, so no question of taking partial with respect to xi and spitting out the derivatives of thereof. Yeah. So what happens to this? It's just the same as the partial of this with respect to its third argument, isn't it? Now this, with respect to its third argument, x, y, xi, and here is the real deal now. So if you're saying that this is an extremal, what must it satisfy? That xi has to be the so-called velocity, again, unless we call x as a time, that term velocity might not make much sense, but the slope of the curve, let's say, y prime. So if you had chosen y is equal to y prime as your, y prime as your xi of the optimal curve, if you had chosen the y prime of the optimal curve here, you would actually have 0. Let's take a pause and try to understand this, what it means. We're trying to give you some insights here to a much bigger result that we will derive for a much more general setting. What this means is that if you have the freedom to choose the third argument of this Hamiltonian independently to make it optimal, the condition that you have to do is to make that a stationary point of the Hamiltonian with respect to the third argument. Not just any stationary point, as we shall see later, this is actually a maxima of the Hamiltonian. So that's where the maximum principle comes in. Okay, we'll of course do this in much greater detail for a much more general setup where you may not even be able to differentiate. The point is not this differentiation. Differentiation is just a consequence of the fact that you can differentiate this here. The bigger point that I'm trying to highlight here is that this is a stationary point, in fact a maxima of the Hamiltonian. So along an optimal curve, if you have that third argument of the Hamiltonian chosen as the slope of that curve, so given a particular x and y and of a particular extremal curve, let's say you are allowed to choose, and this is where the control theoretic aspect begins to show up, because that is the access point through which you are going to manipulate the curve. So xi is your access point to the system. So how will you choose xi so that it's going to still carry you along that optimal? It turns out that if you are living on an optimal or an extremal curve, you should choose your xi to be exactly equal to the slope of that extremal curve, and that will in turn lead to a, okay, I haven't shown that this is a maxima, I have just shown it's a stationary point. Never mind, we will not get into the detail at this point. But the point is it's going to be a stationary point of this Hamiltonian, yeah, and that is in a sense a very rudimentary form of the statement of the maximum principle, which is true in general even if this differentiation is not possible. The idea throughout this course and whatever we do shall be hugely hinged on the fact that whenever you are given a cost functional like so, cook up the Hamiltonian, the third argument of the Hamiltonian, which later on in optimal control will be our control itself, the choice of the control itself. So what should be an optimal control? The very control that maximizes the Hamiltonian, and that maximization need not entail differentiation. For example, if the function is not differentiable, like the modulus function mod x is not differentiable at x is equal to 0, but you still know that it's got a minima at x is equal to 0. So somehow or the other you figure out the choice of this third variable, which later on shall become the control in our case, and find out like what choice is going to give you the maxima of the Hamiltonian. That is going to be your optimal control. Okay, we shall of course have to prove this very rigorously and for a wider class of possible perturbations than we have considered at this point. Remember, when you are dealing with calculus of variations, at the back of your mind you should have this, that you are dealing with only weak extrema, you are dealing with only perturbations that are rather smooth, and you are also dealing with the notion of distance being defined by the one norm. Remember the one norm, the difference between two functions in sense of the one norm is essentially the max of the magnitudes of the function plus the max of the derivatives of those functions. Yeah. So it's not a very rich class of perturbations over which you are considering the setup. In fact, it's nowhere close to giving you conditions for the strong extrema, which only considers the zero norm. Yes. So this is just a hint or a teaser of things to come. We'll have much more to say on this maximum principle. Yeah. Now at this point, you might still be a little uncomfortable about why we use the term momentum. What is this Hamiltonian even doing here? What's its interpretation? At least momentum you understand what it's known as, right? What it's called, what its physical interpretation is. So that's what we're going to try and understand next.